updated the title. So,
okay, I'm going to present this title. Don't worry. Welcome to the afternoon session of the workshop on fluids and PDE. The next speaker is Mimi Dai from University of Illinois at Chicago. And she's going to talk about the heart of causing by coupling.
thank you. Thanks for the introduction. And I want to thank all of the organizers for putting up a virtual platform for the workshop. I can imagine how hard it was. Okay, so yeah, I'm going to speak something on uncoupled systems, and I'm going to focus on MHD system. And since I'm using the Blackboard, maybe it's better I stop sharing. So I guess, yeah. Okay, so. So I'll start with Navier-Stokes, so everybody knows or has seen already in this workshop. So in case I move outside the camera, yell at me. First of all, basic case. And we consider infant pregnancy. Okay, so here we have a moderate understanding about Navier-Stokes equation and its invasive case, the Euler. But there are very interesting questions which are still open. For example, global regularity vs finite time blow up and uniqueness problem for Larry Hope weak solutions. For the invasive case Euler, it's more or less the understanding is at the same level. So we don't know about the blow up. We have local Walpole's, but we don't know about the blow up, and stability is another interesting problem for Euler. It is interesting from the perspective mathematics and physics. Okay, so just to summarize it, so it's relatively well understood with some open questions. And another one to mention is the it's a type of a geometric differential equation. I don't think people from our community are familiar or very familiar with that. So it is the harmonic heat flow onto some manifold. And here in particular, we consider a type of heat flow onto sphere. So the target manifold is a sphere. It has very special geometry. Okay, and the equation is quite simple. And here the D, because it's a map from some random manifold onto a sphere. So the D has magnitude 1. Okay, and how do we get this equation? So basically we have this net energy. And we try to minimize this energy with the restriction of the magnitude being 1. Okay, so we arrive at such a differential equation or partial differential equation. in the geometric analysis community, this equation is very well understood and studied. And so let's just summarize it here. So we know about the singularity situation, okay, both in 2D and 3D, okay. So now I'm going to move on to systems. So here, the first one is MHD. That's a short notation for magnetohydrodynamics. So it's a very important model in plasma physics. Okay, it is a system. Here, it couples Navier-Stokes. That's you. So this is Navier-Stokes, but with a force from the magnetic field. And the magnetic field viscosity. And then consider incompressible case, and the B is great and small. Okay, and here I'll just put this system is a non-structure because it is, and I'll explain to you later. So when you compare Navier-Stokes and this MHD, they look so similar. They have similar nonlinear structures, and they have the same scaling. Okay, so normally you would expect the two theories should be very similar, and most of the time that's true, especially when you talk about positive results like well postings, things like that. But when you talk about global trajectory or stability of fixed points or steady states, then it's very, the MHD is much more complicated. Okay, so stationary solutions and questions related to stationary solutions. Okay. So this is MHD system. Another one, it's a liquid crystal. System. Sometimes we use CD to denote this briefly. Okay. Here it's a coupled system as well. It couples Navier-Stokes and the harmonic map heat flow. So. Okay, it's still there. Okay. And the equation. Okay, so here there are couplings. Here, this one and this one. Okay. And this system, I'll put the same name, but it is amongst the two because in 3D, we don't even know the existence of a Larry Hope weak solution. Okay, so in some sense, this system might be even worse than MHD. Okay, so the difficulties for the systems, of course, besides the nonlinear structure from Navier-Stokes equation, there are nonlinear interactions. So those are resource difficulties. Okay, and so here, in the rest of the time, I'm going to focus on the system of MHD and try to give you some like a simple analysis to show you why it's complicated. Okay. Okay, so now I'm going to erase. So let's look at MHD more closely. Okay. That's where we start from, a energy level, right? So for smooth solutions. So when you look at the velocity component and the magnetic field component, they really have the same scalings and the same structures in the energy law, okay? And a Larry-Hope solution is a weak solution satisfying energy inequality. So we can change here to inequality and in the right space. So finite energy and entropy in R2. So both U and B, okay. So because of this, you do get similarity between results. But most importantly, they are very different. Okay. So the difference it's more important here actually. When you think about the physics, the two systems try to describe, of course, the plasma physics context is very different from pure fluid. Okay. Okay, so then what do we do, right? For MHD, if it's so hard, how do we even like, try to analyze it? So here, there are some strategies, so some attempts. Okay. One very interesting strategy is that we can reduce the system by using some symmetries. Reduction. And the common line is axisymmetric, right? So we know that one. Here are a lot of papers, articles on axisymmetric MHD, and there are interesting results there. If you are interested, I can show you some reference later on my slides. Another one very interesting I want to mention, it's a reduction discovered by Annie, Milton, and Elena. So there's a very special reduction. So you consider a solution of Euler. Okay, actually 2.5 degree sense only depend on the first two components. Okay, so that is a solution of Euler. And then you take the particular form V1, V2, 0, and you take the B to be 0, 0, V2. And you can check this pair exerts. I think Annie and Milton and Elena, they used this nice reduction to show to construct wild solutions in this very particular case, and using the version 1 type of convex integration. It's real interesting. Okay, so that's one way we look for certain reduction, right? And other strategies, we propose simplified models. I'm going to mention two particular ones. 1D model. Another one is without models. Okay, so 1D models of a vorticity form for Euler was first studied or proposed by first studied by Peter Constantine. This was back in 1970s, but recently got very popular again. So here that is for Euler. Okay, so this is, I think I'm out, more or less out. So this is for Euler. Okay. And recently, I think the town hall a group of mathematicians, they studied this a 1D model for Euler equation. Again, they construct or they showed singularity, finite time singularity. Okay. And Directional model, it's another topic with lots of papers, lots of contributions for the pure fluid case for Navier-Stokes and Euler. If I put some names here, it starts from this GOY model and this M model and orbital pi. More recently, like our friend Cascade and Susan and Natasha. Almost out of space again. And Alexei, so lots of them, okay, and the Italian groups.
Yeah, so far, I'm interrupted.
Okay, so and simply summarizing here, for pure fluid, so this is for Navier-Stokes and Euler. The dialectical models are very well understood. Again, from a finite time blow up to vanishing viscosity limit and the global attractor and things like that. So there is a very good picture about energy transfer among shells for the pure fluid case. Okay, so now we are going to propose dialectical models for MHD, inspired by the work for the pure fluid. Okay, so if I go directly to I'm going to show you two particular ones. Okay, so one I call it bidirectional. Okay, and let me fix notation. Take AJ as the energy in the J's shell. Okay. So here UJ is the little Pali projection. Okay. You can imagine in the Fourier space, in the phase space, on the frequency next to J, it's non-zero. Everywhere else it's zero. Okay. And BJ. No square. Okay. And of course, they are functions of time. So, and then those AJ, BJ satisfy a ODE system. Okay. Here J starts from 0. So the AJ time derivative equal to this and minus one. I'll explain the notations more after I give you the equations. AJ minus 1 squared and the magnetic field part. Minus theta. And the BJ time derivative. G squared BJ and minus theta and AJ BJ plus 1 plus BJ. Okay, so I give a name for this system bi-directional energy cascade. So here notation, lambda J we can just take as 2 to the power J. It's the frequency of J's shell, okay? And theta is a very important parameter. It's related to intermittency dimension, n minus delta over 2. So n it's the dimension of the domain where you consider the problem, right? 2D, MHD, or 3D. And delta, it's intermittency dimension. That's very important. And physically, it should be from 0 to n. If it's outside this range, there's no physical limit. Go into details like how it's defined and any properties about it, so not here. Okay, so this is a dyadic model for the MHD system. What is this thing, right? It is a ODE system, and you might think that's very simple since it's ODE. However, it's an infinite system, so there are infinite many ODEs. Good. So here, it is a ODE system, but it's infinite. And that makes things very complicated. Of course, it is simpler than original PDE model. So here, that's what I'm going to say. Compared to the original model, the spatial structure is oversimplified. Basically, there's no spatial structure. And there are models you can actually recover some spatial structure. But anyway, so here, there's no spatial structure. And there's no geometry. Geometry is lost completely as well. It's related to spatial structure. Okay. However, it does preserve some very important features of original MHD. So it preserves the invariance. Okay. Some invariance. In this particular case, it preserves energy and plus helicity. Another feature is that it only captures the local interactions. In the sense that the AJ, so the J's shell only depends on J's shell, the next shell, the previous shell, okay, in phase space. Okay? The same thing here, okay. So you only see the dependence with the next shell. Okay, and of course, it does resemble the interactions of the velocity field and the magnetic field. That's just like the original MHD PDE system. Okay. Okay, so this is one. Very importantly now, I'm going to explain. So here it means directional energy cascade. So when you analyze the sign of these quadratic terms, you realize that some portion of the energy or some nonlinear interactions move the energy to the next level. Some of them move to the previous level, okay? So we have both forward and the backward energy cascade. If I draw a single so that is velocity component and field component. So among themselves, due to the choice of the signs of these two terms, and so here and this, so we have among themselves energy move to higher modes. However, when you look at the interactions of the two, BJ, so BJ is here, it's negative, so it goes to AJ. So it goes here, and the same thing. And there are more interactions from this equation, and you see that AJ goes here. Okay. Here. Okay. So because of these interactions, you get more complicated energy cascade. Okay, for this model. Okay. So next, I'm going to tell you that you can choose your own models, right? So we can, if we switch the sign, this one to negative, here to positive, and here to positive, here negative. Then we get another model. So we get, so now I'm going to erase things we got to need. Sign here is positive. Then we have a model with unidirectional energy cascade. So just a sign change. Okay. Sign change here. Okay. And now if I draw a diagram for the energy cascade, it's similar. So I think so AJ's socks is all right. Okay. So socks, it goes forward, and after the changing signs here, now we get the interactions like that. So AJ goes to BJ, and BJ minus 1 moves to AJ. Okay, so now you see, even we have interactions, but it maintains a forward energy cascade. So it doesn't go backwards to previous show. Okay. Okay. That makes a big difference between the two models. And it's not clear which one is more realistic. And from the point of view of a preserving environments, this model, it only preserves energy, but not so if you ask physicists, they may prefer the first model because it preserves cross helicity. But since from the very beginning we said there's not really spatial structure or geometry, then it's kind of it makes not much sense to talk about cross helicity anyway. So yes, it's hard to tell which model is more realistic. Okay. Okay, so now I'm going to show you why the MHD is more complicated than the Euler and the Navier-Stokes. So we start just from steady states, okay, or fixed points. See, it's not single. So we have a set of fixed points for each model. So for the model with both forward and backward energy cascade, we find steady state particular form here without a force. Okay, so without a force, of course, the trivial steady state is 0. So here, let's add a force. to the velocity component. And we choose a very particular one. We only put a positive force at the first mode, no force at other mode. And in this special case, we can calculate, we can find the fixed points explicitly. So those are fixed points. And of course here, there's a sequence. And similarly for B bar, okay? And it satisfies okay, so for this model with both forward and backward energy cascade, we find a set of fixed points. And if we try to see it, make it a visual, it's a two planes of a hyperbola, okay? That is A for, and of course, in our two. So there are two special ones. These ones corresponding to a fixed point to Euler. So that is for Euler. So it's a fixed point, and it's a positive one. Here is a Euler fixed point as well. So here it's the set of fixed points for this model. And if we look at the model with a unidirectional energy cascade, and compute the fixed points as well. And it's very similar. Okay, no, it's not. Actually, it's not. So it satisfies this. So AG squared plus BG squared is plus equal to that quantity. Okay. So now, because here it's plus sign, the set of fixed points, they actually sit on a circle. Okay. And again, there are two particular ones, the one corresponding to the pure fluid case. Okay. Actually, I want to tell you, we computed in the case of inviscid models. Okay. With the non-zero, you possibly have uniqueness. Okay. But ideal case, you have a set of fixed points. Okay. And again, as I said, for Euler, for the pure fluid case, you only have two fixed points, a positive one and a negative one. Cheskov and Freilander and Pavlovich showed that the positive fixed point for Euler is a global attractor, it's a strong attractor. Okay, so that's a very strong result. But in this situation, we don't know much. What we know is that the linearized system, linearized systems of the two are unstable. So here I'll put it up. So linear instability. Okay, for MHD. And the same thing here as well. So we have So that's a compared to the result of global attractor for Euler. This is just the worst thing you can imagine. So we take the two particular case, right, and we perturb around the two particular points, and we linearize the system. So we simplify them to Directional models first, and then we take the linearized system. So that's really the simplest thing you can imagine. But we have a linear instability. Okay. So you can see now, if we come back to the original Directional model, the nonlinear version, and the original MHD PDE system, the situation is just much more like harder. Okay, if you try to study the stability or instability of some stationary solutions. Okay. Okay. So that is just one fact that convinced me and Susan that the MHD model is much more complicated. So here the result, the instability of linearized system. Okay, so that's a result with Susan. Other than that, we got some other interesting results here. So I think I have some time to present that. Okay. Other results. More results. Okay, so blow up, right? That's what we care about. So here for the model with unidirectional energy cascade. I didn't put it the way forward energy cascade because in order to see that, we need to know solutions are positive. However, for MHD, we are not able to prove that. If you start from positive initial data, solutions can still become negative. Okay? So I won't say it's forward or backward, so just a unidirectional energy cascade. So for that model, we should blow up if the viscosity is 0. In this situation, we have finite time for any intermittency dimension delta. And we have imagine that plane's supposed to dissipate. Okay, but still we are able to prove finite time blow up, but here only for delta less than a number -1. So if you remember what I said earlier, that's not physical, but mathematically, so below this threshold, actually you are able to show finite time blow up in the viscous case. Okay. Right. So now for model with bidirectional energy cascade, so both forward and backward. Can we construct finite time blow up solution? No. Okay. So now you see the difference between two mechanisms in the two models. Okay, so here we don't know, okay, not clear. Other than that, we can show global existence of a strong solution, global in the sense of time. So for both of them. Solutions in the sense they decay. Okay? When the frequency increase, the modes they decay. But under the condition that delta is greater than or equal to 1. So delta, that's the intermittency dimension. Okay. Okay. And another interesting result, it holds both for we constructed non-unique array of solution when the intermittency is less than 1. And we are able to show unique existence and uniqueness array of solution if the intermittency is greater than or equal to 1. And it's quite interesting when you compare the global strong solution and the uniqueness of the array of. They kind of have the same threshold. Okay. But we can't get much indication here for the original PDE model because Directional model really oversimplify lots of things here. Okay. Okay. And all of these results are quite recent as well. And it's with the system. So in the last minute, I want to say that there are many open questions here, even for dyadic models, okay, but for dyadic MHD. So for example, we want to at least know a little bit more about fixed points here. So do we have a attractor here? Possibly not, right? Because of instability. But if it's not, are we able to show instability for the nonlinear dyadic models? Okay. And then we want to know energy dissipation. Do we have anomalous dissipation? Things like that. And that's another very hard question for MHD dyadic models, because here we really don't have a good understanding about energy transfer between velocity and the magnetic field. So the interactions and the couplings just cause too much trouble compared to Euler. Okay, so I think I'll stop here. Thank you very much.
Thank you very much for a nice talk with me. Are there any questions, comments? Well, you can unmute yourself or find time.
Thank you.
I think there is no question. So, thank the speaker again.
Thank you. Do we have poster session today?
No, today no. We finish now, and we resume tomorrow.
Okay,
At
sounds
10
good.
a.m.
See you tomorrow.